Hey guys, Mr. Gucci here. I dropped my pen. Mr. Gucci here, and I'm going to take you through today's notes 5.3 covalent shapes. And I'm going to do it on a separate PowerPoint so I can draw on it. Okay, so let's get to it. Oh, it's been so long since I've used PowerPoint. How do I start this presentation? Is this it? This is it. Okay, guys. So far we've been doing a lot of drawing Lewis dot structures and drawing molecule shapes on two-dimensional paper. But as you know, molecules are actually three dimensions. A surprise, we're all three dimensions. We live in space. Okay? So today we're going to talk about how we interpret these two-dimensional pictures on a page and turn them into three-dimensional shapes. Okay? So we're going to do that using Vesper theory. I know that's not how the letters are arranged, but this is what we call it. Vesper theory, valence shell electron pair repulsion. It's a theory that helps us determine the shape of molecules based on the idea that electrons will repel each other. So groups of electrons around the atom, be them bonding electron pairs or those little lone pairs, those double dots, they are going to push as far away from each other as they can around an atom. And that is what determines their three-dimensional shape. So let me give you an example here, okay? Let's skip this real quick, all right? So, for example, carbon tetrahydride, aka methane, CH4, okay? There are four groups of electrons around that central atom. And so they spread out in this four-sided triangular pyramid shape that looks like this. We call this shape tetrahedral, okay? And there's actually a cool simulator that I'm going to link to in the notes today that shows us how this works, okay? So let's see here. Let me open up this. Okay, cool. So take a look. Here we have a methane molecule, all right? And this is how the hydrogens space out. This is as far as the hydrogens can be away from each other. So even though we call it CH4 and kind of have the C in the middle and the H's on all four sides, well, look what happens if we try and drag one of the H's to make like a four-sided shape. Oh, look, see if we try and make it flat, the other atoms will move around, all right? They are finding a position that's as far as they can be from the other atoms, all right? And so if you have a central atom with four things bonded around it, we end up calling this a tetrahedral shape, all right? This is as far as the bonding atoms can be away from each other, okay? Let's take a look at another one, okay? Another one would be this, formaldehyde, CH2O. This is three groups of electrons bonding around a central atom, right? There's two single bonds, and then there's a double bond right there. Now, if there's three bonds going on around a central atom, they kind of spread out into a flat triangular shape that we call trigonal planar. So if there's three things going on around the central atom, we call it trigonal planar. Let's take a look at an example from that same simulation website. Let's see here. Is there a trigonal planar one here? Slightly different, but yes, there is. Okay, so here we go. So here is a trigonal planar molecular shape. Now look, you have a central atom and you have three things going on around that central atom. And so these guys are going to space out as far as they can. And that just happens to be in this flat triangular shape. If you were to try and move one of these guys towards the others, they would instead repel and assume a new position that was far away. Okay, so this is trigonal planar shape. Okay, let's take a look at another one. Okay. Here we have carbon dioxide, okay? Carbon dioxide, CO2. This carbon dioxide has two groups of electrons around the central atom. It has a double bond over here and a double bond over there. And now because there's only two things going on around the central atom, those two double bonds are going to move to opposite sides of the carbon. They're going to space out as far away from each other as they can. And we call this a linear shape molecule. Okay, linear shape. Again, there's only two things going on around this central carbon. There's a double bond on one side and a double bond on the other. So they will move to opposite sides of the carbon. I know for a fact they have something like that here. Let's take a look here. Carbon dioxide. Great. So take a look. A double bond and a double bond. These guys are going to be on opposite sides of the central atom. And if you try and move one, the other moves as well. All right. So if you try and get them closer, the other one will space out again. They are linear shape. Okay. They are linear shape. Now, next one is water. All right. Water. Now, water molecules have this shape. Despite having only two bonds coming off that central atom, for some reason, they are bent closer together. They don't stretch out and stay exactly linear like a carbon dioxide. Why? Well, it makes sense if you look at, by the way, call the shape bent. It makes sense if you look at a Lewis dot structure, all right? Look at this Lewis dot structure and you'll see that these hydrogens aren't the only thing going on around this central atom. There are two lone pairs that you would also draw that are also there around that central atom. And one second, I'm going to sneeze. Bless me. All right. Yeah, so these electrons here, these lone pairs, they are also things going on around that central atom. So even though you don't see them in the molecule itself, they are there. And since they are also electrons, they are repelling the other bonds away from them. Okay, so there's four groups of electrons around the central atom. There's two single bonds, and then there's two of these lone pairs, and the lone pairs push the other electrons away. Let me show you again in this simulation. Okay, let's see here. Here we go. All right, so take a look. Take a look. So you have these two bonds, okay, and then you have what you can't see is these lone pairs of electrons that are also circling around the oxygen. Now, they wouldn't be this far out. They would be a little bit closer, but this allows us to manipulate them. All right. Oh, take a look. So I can make the lone pairs invisible. So now you're like, oh, Mr. Gucci, why does this continually end up in a bent shape? What's going on? Why is it bending like this? Well, it's bending like this because these lone pairs, these invisible lone pairs, are here interacting and affecting the bond, okay? So even though they are invisible, they are affecting the shape of the molecule. All right, let's see if I can find another one. All right, here's another one, right? So here, for some reason, we have a central atom and three guys coming off of it, but it's not flat. It's not flat. And the reason why it's not flat, the reason why some of these atoms are kind of flexing downward is because, again, there is a single lone pair on top, a group of electrons that you can't see, but it is working to deflect those other atoms there. Okay, so all these guys are repelling each other, and they're just going to arrange around the central atom in a way that they think will get them farthest away from each other. Okay, cool. Close this. Yeah, close this. Don't save. Cool. All right. So again, even though carbon dioxide and water both look like they just have two bonds coming off that central atom, the fact is that water also has some lone pairs that are present that you can't see that are deflecting those bonds downward, giving it a bent shape. Okay? So these things going on around the central atom, whether they're bonds or lone pairs, we call this the atom's steric number. All right? The steric number is the number of electron groups that are coalescing around the central atom. Now, what counts as an electron group? A lone pair, two dots, that counts as one group. All right. A single bond counts as one item. All right. A double bond counts as one item, and a triple bond counts as one item. All these things only count as one value for the steric number. They all count as one thing for the steric number. So here's the sample question. How many things are going on around this central atom? What is its steric number? Remember, lone pairs, single bonds, double bonds, triple bonds, they all count as one thing each. So if I look at this, am I going to be able to draw? Am I going to be able to draw on this? God help me, can I draw on this, please? Okay, I guess I'm going to have to draw on it like this. Okay, so here we go. Let's blow this up. All right, so here we go. So drawing So here is the central atom. And let's count the number of things that are going on. 1, we got a lone pair. All right. 2, we got this bond. 3, we got this bond. And 4, we have this bond. So we have 4 bonds, or 4 things. So the steric number is 4. That is the steric number. All right, let's take a look at this one right here. All right. So here we go. Again, we look at the central atom here, which is the carbon. How many things are going on around this central atom? Well, this bond counts as 1. This bond counts as 1. And this double bond also counts as 1. Each of these counts as one thing going on around the central atom. So we would say that this has a steric number of 3. Steric number of 3. Okay? Now, figuring out the steric number is the first step in figuring out what shape these molecules are. What shape these molecules are. So here's what you're going to do. To determine the shape of a molecule, you are going to first find the central atom. Okay? Next, count the lone pairs, the bonding groups. Count up everything around that central atom that's happening. Okay? Next, use that information and consult the following table to tell you the shape. Here is this table. Okay, let me make this full screen. So here is the table, okay? If you have only 2 things going on around the central atom, i.e. a steric number of 2, you are a linear shape molecule. Okay? If you have 3 things going on around the central atom, then you are steric number 3. Okay? All right? And you would be trigonal planar. But if one of those items is a lone pair that you can't see, then it will appear bent. All right, again, it appears bent because, oh, you got a lone pair of electrons here that you can't see, but they are exerting a force, a repulsive force, onto those other bonds. Okay? If you got 4 things going on around your central atom, can I erase? Yeah, cool. All right. If you got 4 things going on around your central atom, then you are tetrahedral. But if one of them is a lone pair that you can't see, then it looks like this, and we call it trigonal planar. Again, you can't see these lone pairs on top, but they're there, and they are acting on the other bonds, okay? You can even have 2 lone pairs on top. 1, 2, all right? Which are acting on those bonds to push them away. This is water, all right? Water is actually basically a tetrahedral shaped molecule, but it just so happens that 2 of those things on the tetrahedron you can't see. All right, so this is what water is. Okay, so let's take a look at this. Okay, so what is the shape of this molecule? Count the things around the central atom, and then subtract from them the lone pairs to see where you end up on this table. So this is the same thing as before. If I look at this, we have got 1, 2, 3, 4 things going on around the central atom. So we're here, okay? We are in this row. Now, how many of them are lone pairs that are invisible to us? One of them is a lone pair that's invisible to us. So we're in this column. So down here. This is a trigonal pyramidal shaped molecule, okay? Let's try another one. All right, let's try another one. Here we go. Now, you're going to instinctively want to say, this is linear, Mr. Gucci. It's linear because this thing is in a straight line. So it's linear because that's what it's on the paper, Mr. Gucci. What's wrong? No. Follow the steps, all right, guys? Follow the steps. What is the shape of this molecule? Well, first of all, count the steric number. Count the number of things going on around the central oxygen. We've got a lone pair, a bond, another lone pair, and another bond. So we have 4 things going on. So already can't be linear. Okay. Now, how many of those things going on around the central atom are invisible lone pairs that we can't see? We got 1 invisible lone pair. We got 2 invisible lone pairs. So we're in this column. So this is going to be a bent shape molecule. It's going to be bent, okay? Let's try one more. Let's try one more, okay? So we got this guy right here from above, okay? So first step, count the steric number around the central atom. Count the number of things that are happening. Well, this bond is one thing. This single bond is another thing. And this double bond is still just one thing. So we have 1, 2, 3 things going on around the central atom. So we're going to be in this row right here. How many lone pairs are invisible to us? None. There are no lone pairs that are invisible to us. So we're going to be in this basic geometry column. So this is what we would call trigonal planar, okay? And that is how you're going to do your homework. I think that's it. Is that it? Yeah, that's it. All right, guys. So this is your notes video. I'm going to upload this with the daily roundup. And now I'm going to do a homework help video, okay? Good luck. Gotta stop this. How do I stop it? How do I stop it? How do I...